So today we're looking at our second set of notes over solving trig equations. In our first set of notes, we looked at some of the basic techniques for solving trig equations. And those were just using our opposite operations like adding, subtracting, multiplying. We did a couple with square roots. And then we looked at one where we had to just factor out the greatest common factor. So in today's notes, we're going to be looking at a couple more, little bit more complicated techniques. Now, the first way that we're going to look at is when we're talking about an equation of a quadratic type. So an equation of a quadratic type is an equation that can be written in quadratic form. So remember, we're solving here, and we're using a lot of the same algebra techniques that we've used in the past. And so why this can be helpful is because we know a lot about quadratics. We know how to factor, we know how to compute the square, we know the quadratic formula. So if we can write an equation in quadratic form, it gives us a lot of options. So in the past, when we've seen quadratic equations, they've looked like x squared plus 2x minus 1 equals 0. That's a pretty standard quadratic equation. But remember, it doesn't always have to be an x. I could have things with a's or other types of variables. Basically, what the quadratic form is that it's something squared, something to the first power, and then a constant. Okay? But now, remember that that constant is sometimes 0, but for the most part, we're looking at some constant number. And so this could be anything. So even if I had something with stars, if I had star squared plus 3 star plus 1 equals 0, that's still in quadratic form because I have something squared plus something to the first power plus 1. So for us, particularly when we're looking at trig equations, the thing that's going to be being squared and then to the first power is going to be a trig function. So like sine squared plus sine plus 1 equals 0. And like I said, the reason that we want to look for these patterns or this form is because we can use some of those techniques that we've looked at previously. So let's look at an example. So here we have 2 sine squared, x minus sine of x minus 1 equals 0. So our first thing we should notice is that we do have a squared, okay? And we can't factor out the sine as a greatest common factor because we do have a constant of 1. But what we should notice is that this is in quadratic form because I have 2 sine squared minus sine and then my constant. So what I'm going to do is similar to what we did when we looked at simplifying trig expressions, is I'm going to come over to the side and say, okay, let's think about this if I just had x's instead. So 2x squared minus x minus 1, and how would I solve that problem? Well, just like with any quadratic, our first goal is to factor if at all possible. So in this case, I would want to use the AC method. So I would say, what's going to multiply to give me negative 2? That's going to add to give me negative 1. Well, that's going to be a negative 2 and a positive 1. And then we're going to factor that by grouping. Remember, I break apart my first term, or my middle term, using the 2 numbers that we just found. And then I'm going to group my first 2 together and factor out my greatest common factor. Group my second 2 together and factor out my greatest common factor. And then what I have in parentheses should be the same thing, which in this case is x minus 1. So then we're able to factor out that x minus 1, and we're left with 2x plus 1. And then that is our factored form. But for us, remember that we don't have x's, we have signs. So it's going to factor the same way, just instead of an x, I'm going to replace that with our sign of x. Now, realize that you could go through all of the same factoring steps with the signs in there. You could break it apart using like -2 sine of x plus sine of x minus 1. It just gets a little confusing because it's a lot of signs. And so that's why I think it's a little bit easier to kind of go off to the side and look at it with just x's instead. Now, from here, again, we can kind of think about our quadratics. Once I have something factored, as long as my factors are set equal to 0, which in this case we are, we can set each of the factors equal to 0 separately. And then from there, it looks very similar to the equations that we saw in our first set of notes. So I can just use opposite operations by adding 1. And then on our second one, we would subtract 1 and divide by 2. So remember that we kind of have two ways that we can try and solve our trig equations. Basically, we're working our way backwards. Remember, instead of plugging in an angle and looking for a number, I'm trying to work my way backwards and say I need to solve for x, which in x here is going to be an angle. So what angle, when I plug it in for sine, gives me 1 for my first one and -1/2 for my second one. So remember, the first way that we can look at these is to look at our graph. So remember, for our sine graph, it goes through 0, 0. It's going to end at a 0 at 2 pi. At pi, we have a 0. And then halfway in between those are our minimum and our maximum. Well, if I'm wanting to look for where sine of x equals 1, I'm looking for this point right here, because remember, my maximum occurs at 1. So we need the x value that occurs at. Well, remember that if my third 0 is at 2 pi, my second 0 is at pi, I know halfway in between 0 and pi has to be my maximum, which is going to be at pi over 2. So I know that for my first equation, I get x equals pi over 2, and then remember, we do want the general solution, so it's plus 2 in pi. Now, for our second one, we're looking for where it equals -1/2. So again, looking at our graph, -1/2, I have two different spots this time. And it is going to be after pi, but it's a little bit harder to tell what my x values are going to be for that. So remember, the other way we can do it is looking at our unit circle. So remember, for our trig functions, all of our trig functions are positive in our first quadrant, sine is positive in our second, tangent is positive in our third, and cosine is positive in our fourth. So because we want a -1/2, we're looking in our third and fourth quadrant. And because it's a 1/2, we want to think about and kind of work our way backwards. What angle gives us a +1/2? Well, if I was in my first quadrant, hopefully we remember that pi over 6 is what gives us 1/2. So if I was looking at the angle pi over 6, sine of x equals a +1/2. So basically what we need to do then is that's going to be our reference angle. So we need to find the two angles in our third and our fourth quadrant that have pi over 6 as the reference angle. And remember that the nice thing about our radian measures is that for anything on the unit circle, the reference angle is going to have the same denominator as the original angle. So if I'm in my third quadrant, remember that it's 1 more than the denominator on top, so that would be 7 pi over 6, because I need a reference angle of pi over 6. And then in our fourth quadrant, it's going to be 2 times the denominator minus 1. So it's going to be 11 pi over 6. And so just like with our quadratics, where we get 2 answers, in this case, for this trig function, we have 3 sets of answers. Now remember that because our equation goes on forever, there's technically an infinite number of solutions, but they do have to be in this form. And so that's why we go ahead and write our answers this way. Alright, so on our next one we're looking at, again, we have a quadratic here because I have that sine squared. The problem that we run into is that just by looking at this, we have 2 sine squared plus 3 cosine. Again, we have something to the second power, something to the first power, and a constant. But the problem here is that what's being raised to the second power is not the same thing as what's being raised to the first power. And so basically this would be like having 2x squared plus 3y. I can't factor that if they're not the same. And so this is where our last unit really comes in handy, because what we're going to do is we're going to think, okay, I have a sine and a cosine right now, but is there a way that I could switch one of those to be the other? That way I do have the same trig function throughout my equation. And hopefully when we see that sine squared, it automatically should kind of trigger our Pythagorean identity, which is sine squared plus cosine squared equals 1. Now, since we don't have a cosine squared, we're not going to be able to use that portion. However, we do have a sine squared. So I'm going to solve for sine squared, and we get 1 minus cosine squared equals sine squared. So we're going to substitute that in for our sine squared. But be careful because that 2 is still on the outside. So we are going to have to distribute that before we can start trying to solve. So we end up with 2 minus 2 cosine squared plus 3 cosine minus 3. So then combining my like terms, and then my last step is we could technically factor this and it would be fine. The only thing is most of the time it's usually a little bit easier for us to have a leading coefficient that is positive. So I'm going to go ahead and move all 3 of our terms over to the right-hand side. So I added the 2 cosine squared of x, subtracted the 3 cosine of x, and added the 1. And then from there, it's going to be pretty similar to the last example that we did. Just this time we have cosines instead. So I'm still going to come over to the side, because it's a little bit easier again, I think, if I'm looking at 2x squared minus 3x plus 1. So again, I'm going to use my AC method. So I'm looking at what multiplies together to give me 2, that adds together to give me negative 3. Well, that's going to be negative 2 and negative 1. So again, I'm going to break apart my middle term and then factor by grouping. So we have x minus 1 times 2x minus 1. And again, we don't actually want x's, we want cosines of x. So I'm going to go back in and replace those x's with my cosines of x. So then, once it's factored, we can set each of our factors equal to 0. And then use those opposite operations. So cosine x equals 1, and cosine x equals 1/2. And again, if we wanted to look at our graph for that first one, remember that the different thing about our cosine graph is that it starts and ends at a maximum. Halfway in between is our minimum. And then halfway in between those is our 0. So we want to look at the first spot that cosine of x equals 1, which notice is going to be at 0. So we would say x equals 0 plus 2n pi. But notice that we could also just simplify this to be 2n pi. Then our next thing that we're looking at is cosine of x equals 1/2. Again, we're going to have two places that occurs. So again, we could kind of try and figure it out from our graph, but it's not going to be quite as nice. So again, we can always refer back to our unit circle. So because we have a positive 1/2, we're looking in our first and our fourth quadrant. And this time, since cosine is what equals 1/2, we know that we're looking at pi over 3's this time instead. So because we're in the first quadrant, our first answer is just going to be pi over 3 plus 2n pi. And then we need to think about what angle in my fourth quadrant has a reference angle of pi over 3. Well, again, remember that in our fourth quadrant, our numerator is 2 times our denominator minus 1. So it would be 5 pi over 3. So again, we have 3 answers that would solve this equation. Alright, so in this one, let's look at another technique. So notice here that we don't have anything that's being squared, so it's not going to be in quadratic form, so we're not going to use that technique. Okay, and just so that we kind of get the practice for it, let's go ahead and solve this in degrees. So this time, instead of giving the general answers, I'm going to specifically give the answers that are between 0 to 360. So our first step is, okay, no, it's not in quadratic form, so we can't factor it that way, but hopefully we notice that both of our terms have a cosine of theta in common. So we can factor it that way. from there, we're going to just do the same thing that we've been doing. I'm going to set each of my factors equal to 0. So on our first one, we have cosine of theta equals 0. Again, thinking back to our graph, remember that I'm going to start and end at a maximum for cosine. Halfway in between is going to be our minimum, and then halfway in between those is going to be pi over 2 and 3 pi over 2. But remember that we are talking about it in terms of degrees this time. So pi over 2 is going to be 90 degrees. And 3 pi over 2 is going to be 270 degrees. We don't have to worry about the plus. In this case, it would be 360 in, because we're only solving between 0 to 360 degrees. Now, our second one, we do need to do some opposite operations. So we would subtract 4 and then divide by 5, so we get negative 4/5. Now, hopefully we noticed that negative 4/5 is not on our unit circle. Again, you could try and look at your graph, but you're not going to get an exact answer. So we're going to think back to one of our previous units and think about, okay, if I can't work my way backwards using my graph or using the unit circle, I'm going to have to do something different to get rid of that sign. Now be careful, because a lot of people want to divide by that sign, but we can't do that, because remember that sign is an operator, just like a square root of x. I can't divide by a square root of x because that's not the inverse of a square root. Squaring is the inverse of a square root. Just like this, sign is an operator. I cannot divide by that sign because that's not the inverse. My inverse of sign is inverse sine. So I'm going to take the inverse sine of both sides. And when I take sine inverse of sine, I will get just theta. And then we have sine inverse of negative 4/5. Now, if I asked for the exact answer, that would be your last step, because our next step is to plug it into our calculator, and it's going to give us a decimal approximation, which will not be exact. So for us, if I asked for the exact one, that would be it. Now, if I just said find the approximate answer, rounding to, the nearest whatever, 2 decimals or something like that, then we could plug that into our calculator. So for us, what we're looking at, I'm going to click my second button, then my sine button, and then type in negative 4 divided by 5. And we should get that theta equals negative 53.13 degrees. Now, if you didn't get that, go into your mode and make sure that we're in degree mode, not in radian mode, and then try it again. Now, something to be careful about here. Why did they give us a negative answer? Well, remember that whenever we looked at the inverse trig functions, we had to make those functions one-to-one, which meant that we had to limit or restrict the domain of our original function. And for sine, that domain was between negative pi over 2 to pi over 2, or in degrees, negative 90 to 90 degrees, which is why they gave us that negative 53 degrees. However, we don't want to leave it as a negative for this answer because they ask us for the answers between 0 and 360. So basically, we need to find the positive equivalent, or in other words, the coterminal angle. So remember that we do that by adding 360 degrees. So if we take that and then add 360, we're going to get 306.87 degrees. And that would be our answer. However, we do have to take it and think about our steps one more time. So what we need to do is think about, okay, if I'm talking about sine, and we're looking at a -4/5. If I was thinking about my trig functions, okay, we got our answer in the fourth quadrant, because 360 is in our fourth quadrant. And when we were dealing with our inverse trig functions, we only wanted that one solution. However, because now we're solving a general equation, we want all of our solutions, we have to think about, is there anywhere else that would happen? And there is, because notice that sine is going to be negative in my fourth, but it will also be negative in my third quadrant. So the 306.87 is what gives us our fourth quadrant one, but we also still need to find our third quadrant one. Well, it's actually going to be easy enough, because if we think about it, if I have an angle here, and we need it to have the same reference angle in my third quadrant, we're going to have something that is exactly 90 degrees apart. So we could subtract 90 degrees and get our last answer, which is going to be 216.87 degrees. Now, I know that's a lot of steps, and it's kind of a lot to think about, but we just have to kind of be careful and think about, if I'm now looking for all of my solutions, you have to realize that our trig functions, because they're periodic or they kind of repeat themselves, we're going to have multiple places that could occur. And so we need to make sure that we're thinking about the steps that we need to do in order to find all of those places. Alright, so our last type that we're going to need to look at is, what do we do when we have things that are being multiplied or divided on the inside of our trig function instead of on the outside of our trig function? And they're not super hard, we just have to approach them a little bit differently. Now, for the first half of the problem, it's going to be very similar to the ones that we've been doing. So in this case, notice we have a 3 tangent of x divided by 2 plus 3. So our first goal is still going to be to isolate that trig function. So I need to subtract my 3, divide by 3, and I get -1. And from there, again, we want to think about, okay, going back to our graph, remember that our tangent has asymptotes at -pi/2 and pi/2. which means that exactly halfway in between the negative pi over 2 and 0 is going to be that point that we need, which is at negative pi over 4. But remember, because we're talking about equations, we want the same angle but the positive one. Well, hopefully we remember that negative pi over 4 is going to be in our fourth quadrant and have a reference angle of pi over 4, which would give us 7 pi over 4. So that's going to be one of our solutions. But because tangent is also going to be negative in our second quadrant, again, thinking back to the fact that we're going to have multiple solutions because we have a trig function, we have to list all of those. So we need to list the angle in our second quadrant that has a reference angle of pi over 4. And that's going to be 3 pi over 4. Now, the difference that comes in now is that whenever we take tangent inverse of both sides, that's what gives us that 3 pi over 4 and the 7 pi over 4. And that's what's going to undo the tangent that we had. But because when we undo the tangent that we had, we're just going to be left with what's on the inside. So before now, it's just been x or theta. What's different here is that now we have a divided by 2. So basically we have to take one step more and solve for our x. So we're going to need to multiply both sides by 2 in order to solve for x. So once we do that, notice we would have to distribute it to both our original angle, but also the period that we're talking about. So if I multiply the 2 to the 3 pi over 4, my 2 would reduce with the denominator. So we end up with 3 pi over 2. And then 2 times 2 gives me 4 in pi. And the same is going to be true for our second answer. I'm going to get 7 pi over 2 plus 2 in pi. So again, not super different or super complicated. Basically, we just kind of have to think about one last step of getting rid of that 2 that we had on the inside. But please be careful because you do have to multiply that 2 after we've gotten rid of the tangent. We cannot multiply the 2 and say tangent of x equals negative 2 because if it's on the inside of a function, it cannot be removed until that function is undone. So let's look at one last example. This says solve for all solutions between 0 and 2 pi. So we're back to radians, so that's fine. This time we are looking for all of the solutions just between 0 and 2 pi. Again, I have a 3 on the inside, so we're going to be using that same type of...
Tammy Davis, please report to the freshman office. Tammy Davis, please report to the freshman office.
Same type of idea that we're going to need to divide by 3, but remember we have to do that as our last step. So my first step is going to be to divide by 2. So we're looking at where does cosine equal 1/2. Well, cosine is going to equal 1/2 at pi over 3. And then it's also positive in our fourth quadrant, which would be 5 pi over 3. And you might say, wait, it said just to find all the solutions. I don't need to worry about the plus 2 and pi. But because we have that 3t on the inside, I'm going to put that plus 2 in pi there until we get the t completely by itself, okay? So we're going to divide by 3 this time to both sides to get rid of that 3 that's being multiplied. Well, remember that dividing by something is the same thing as multiplying by the reciprocal. So I'm going to go ahead and put times 1/3. So we're going to get pi over 6 plus 2n pi over 3, and then 5 pi over 6 plus 2n pi over 3. So, now, like I said, we were waiting until we dropped that 3 in order to start writing our solutions. So pi over 6 and 5 pi over 6 are our solutions. However, again, it's kind of that catch. Notice that this time our period is different. Our period is basically 2/3 pi. And because of that, we're actually going to have some extra solutions between 0 to 2 pi. Because basically it's going to repeat itself more before we ever get to 2 pi. So we have to go ahead and find those remaining solutions. But again, since it's only between 0 to 2 pi, we don't have to worry about plugging in negatives. If we plugged in 0, that's what's going to give us the pi over 6 and the 5 pi over 6. If we plugged in 1, notice that we would get pi over 6 plus 2 pi over 3. Remember, when we're dealing with radians, we're basically just dealing with fractions, so we need to find a common denominator. So we would get 4 pi over 6, so we get 5 pi over 6. Which, since we already have 5 pi over 6, that kind of takes care of it the first time that we list it. But we do need to go to our next one, which is the 5 pi over 6. Again, we're going to plug in a 1, so we have 2 pi over 3. So we get 9 pi over 6, but notice that we can reduce that to be 3 pi over 2. And then we need to keep going because we need to think about, okay, what would happen if I plugged in a 2? Well, that would give us pi over 6. And I would multiply 2 by 2, so I get 4 pi over 3. Again, finding a common denominator.
Don Rose, please contact the freshman office. Don Rose. Thank you.
Well, we get 9 pi over 6, which again reduces to 3 pi over 2, which we already have. So we don't have to worry about writing it again. But then we do need to do our last one. And we get 13 pi over 6. And notice that 13 pi over 6 is going to be bigger than 2 pi, so we don't have to include that one either. Going back if we plugged in a 3 now, notice that 2 times 3 gives us 6
Hayden
pi.
Delno, if you are in the building, please come to the front office. Hayden Delno, if you are in the building, please come to the front office. Thank you.
Notice that we would get 6 pi over 3. Well, 6 pi over 3 reduces to 2 pi. And since I'm only wanting the answers between 0 and 2 pi, anything that I add to 2 pi is going to make it bigger than 2 pi, obviously. So we know that that would be the last of my solutions. Now, if we did want to go ahead and check ourselves, remember that you always have the option to plug this into your calculator. So you could take 2 cosine of 3t and then plug in 1 as well and see where those two lines, the line and the graph of cosine are going to intersect and make sure that we have all of your solutions. Now, I won't give you a ton that are like this because it is a little bit more complicated. You do have to take a couple more steps, but you will see some of this type of things in some of your upper level or your next math classes. So I at least wanted to show you an example of how this might work. And again, remember that with all of these, it comes back to, since your trig functions are repeating themselves, we have to make sure that we're finding all of the possible solutions, either to make our general solutions where we add the 2 and pi, or given a specific range like 0 to 2 pi, that we're finding all of the solutions for that.